Hello.
Hello.
Good afternoon, Mr. Hidhamsu.
Hello, everybody. Okay,
Yes, we're fine. How are you?
I'm fine, thank you. Okay, let me first introduce myself. I'm Andreas Chrysanthou. I'm an instructor in the Cyprus Maritime Academy of Intercollege Nicosia here in Cyprus. And today, I would like to invite you to a lecture, an introductory lecture actually, which is addressed for the candidates of the certificate of competency of officers in charge of an engineering watch, which is a course that a 3-year course that is offered by the Academy. And of course, one of the years is compulsory practice on ship, which is mandatory. And I hope you will enjoy it. Well,
Thank you very
today
much.
we are going to talk about a very important subject in thermodynamics, which are the thermodynamic cycles. And in particular, these two cycles, the power cycle and the refrigeration cycle, which together constitute a great deal of the happenings in life and in engineering, from power, electricity generation, motion, process cooling and everything, human comfort. And we are going to see how all this fit together. But before we do, that, we have to go a little bit into the first principles to understand how this cycle works. And to do that, we have to see what can be done and what cannot be done in thermodynamics. And this, we call everything that's happening in thermodynamics, we call them processes. And here we're talking about reversible processes and irreversible processes. As you know, all the processes in life are irreversible processes, but for the sake of clarification and definition, we'll be dealing with reversible processes here. A reversible process is a process which starts from one position, one state, goes to another state, and then is able to come back again. It's like ice and water. Water turns into ice by removing heat, and then by adding heat, you can turn it back into water again. While an irreversible process is a process that cannot come back to its original state, and this is usually frictional losses and things like that. For instance, if you rub your hand on the table, you can feel the heat. That heat which is generated is lost into the atmosphere, and there's no way this heat can come back into your hand again. Okay, having said that, we are going to look how these processes fit into this framework. Now, as you know, things are changing with various conditions, with temperatures, with pressures, with volume. And one way to do that is to see how these processes vary on a so-called PV diagram, which is a pressure volume diagram. Now, various people have done these experiments and these principles, and there we can see a process which runs on a constant temperature line. This is called an isotherm, a constant temperature. And there we can see how this is related. Now, this is in fact called the Boyle's law. And if we go to the other side here, we can see the process happening on a constant pressure. And this process is called isobaric process. And you can see how the volume changes with respect to time and at constant pressure. This is an isobaric process. The same way here, we can see a process done on a constant volume, and this is called an isochoric process. And down here, you can see a process which is called a adiabatic process, which is the Poisson law. Now, these processes obviously are happening on substances. Now, substances basically can be various things. Can be gas, can be liquid, it can be a mixture. It's like having, how water is changing when pressure is changing, when you are adding heat. So when we're talking about a process here, we're talking about the state of a substance changing along a particular condition. Now, here in the middle, we have a cyclic process, which basically means that a particular substance goes through various such processes, starting from a particular point, and then coming back to the same point again. This is called the cyclic process. And this is what we are going to see mostly today. All the cycles that we are dealing today are all cyclic processes. And this is how the whole engineering setup is made. Is that clear so far? Any questions up to here?
It's okay, thank you.
I would like to ask one question, Mr. Andreas.
Okay, please.
Regarding these cycles,
Yes.
do we have any conservation of energy?
Yes, we do have conservation of energy in the cycle, and it's a good question. We are going to have a look at it actually later on in the lecture. Indeed, that's where I'm going to base our discussion. Everything has to do with the conservation of energy. But let me allow me to show that as you go along, and you will understand it better. Is that clear?
Thank you very much. Yes.
Okay, good. Okay, having said that, a particular scientist called Sadi Carnot at some stage conceived a series of such processes and developed a cycle, the so-called Carnot cycle, which, as we can see here, if we can represent it on the pressure volume diagram again, consists of a process starting from a particular point in universe and goes down an isotherm, and this is like, for instance, having boiling of water in a boiler by adding heat, then goes down an adiabatic expansion. This is something like the expansion happening in a turbine or something like that. Then you go back into compression, condensation, which is a process where we remove heat in a condenser. That's something I'm trying to relate it to something practical. And then the process is completed by compression back to pumping the water back to its original state. So here you can have a cycle which starts from point A and again goes to B, C, and D, and then back to A. And there you can see that during these four processes, there is some work and some heat associated with them. And in particular, you can see that heat can only occur in only two of these processes, the two isothermic processes. That's where we add heat, and that's where we subtract heat. That's adding heat in a boiler or subtracting heat in a condenser. And all four processes have some work done with them, either useful work done, which is a plus sign, or minus work, which is a work given to the system. Now, in order to do that, you can see clearly in another example here that is not only related to power generation, the Carnot cycle, but you can see how it's happening here in the case of a piston. You can see that especially if you notice this part here, which is the expansion, and you notice during the expansion, the piston goes down. At this point, the system does work on the environment by turning the crankshaft, and this in turn turns the engine. So this is this part here, which is the system provides useful work to us. Going back on the other side, compressing back, is just to bring the system back to its original state. Okay. If we go around the cycle now, as we have here, we can see that applying the first law of thermodynamics, which says that in a cycle, and this is the conservation of energy, as you have quite rightly said before, during the cycle, whatever we give into the cycle is equal to what is given out and what remains within the system. So this is heat, this is internal energy, and this is the work done by the system. So if we go all this, look at all these four processes, we'll see at every process what is happening. And at the end of the day, we see that the cycle here tells us that all the heat output in is converted into work. Well, we all know that this is not possible. This is restricted by the second law of thermodynamics. But this is why the Carnot cycle is only a theoretical cycle and provides us the basis for analysis. But we can see that a bit later on why this is not the case. Okay. Is that clear? Yep.
I have one question, Mr. Andreas.
Yes.
Because you told us that there is work being produced, it means that in any slight change in temperature, are we going to have work production? And for example, a machine will be able to run, or we need to have like a specific difference in temperature, in order to achieve this movement?
Yeah, this is quite right. Yes, it is true. We are going to see this in the next couple of slides. It is a consequence of this of the first law of thermodynamics that when we come, it's a natural process. When you come from a hot reservoir to a cold reservoir, which is basically going from a boiler to a condenser, when we go into that process, then there is always useful work done out. Otherwise, we wouldn't be able to have electricity generation. But we are going to have a look at it in the next couple of slides, how this is actually achieved. Is that clear?
Yes, very clear. Thank you.
Okay.
Yeah, it's fine.
Pardon?
I said thank you. It's fine.
Okay, good. Right. What we have here, we have seen the changes happening on the pressure volume diagram. However, scientists we like to see them done in a different diagram, like the temperature entropy diagram. The entropy is another form of it's a form of energy. We're going to deal with this lady a bit later on, anyway. So, as you can see here, the temperature entropy diagram gives us a cycle in a slightly better format. And the bell-shaped figure that we see here is indeed, it shows us the phases that the substance undergoes during the change. So you can see that on the left-hand side of this diagram is liquid. Here in the middle, all here in the middle is a mixture, liquid plus vapor, say. And on the right-hand side is gas. So if something is moving along this way by adding energy, entropy's energy, we can see how this changes. So it's a better representation from the pressure volume diagram, and this is how the TS diagram, as you call it, is preferred. However, there are some restrictions. As you can see from here, having looked at it in the TS diagram, we can see definitely some problems with the theoretical Carnot cycle. Here we can see how it is represented on the TS diagram, and here we have on the right-hand side an actual system which such cycle is implemented. And in fact, this system is a representation of a power station, electricity generation station. And there we can see that that's the process where we add heat, the boiler. We produce steam. The steam is then is expanded through the turbine down here, and goes into the condenser. And this is the area where you made your question previously, that when you move from a higher temperature to a lower temperature, there's always useful work done. Now, during the expansion, the turbine turns the shaft, which in turn turns the generator to produce electricity. This is the useful part of the station. Now, going back here in the condenser, it's this part here on the cycle, we condense that back to liquid form for the pump to pump it again back to the boiler. However, here we can see automatically some practical problems. These two systems here, the turbine and the pump, cannot operate in a two-phase mixture. This is a two-phase mixture. As you can see, it's a mixture of liquid and vapor, and these two systems cannot operate on that. They need any droplets or any traces of mixture, then they will cause any pinging of the turbine blades, and on the case of the pump, it will cause some cavitational problems. So this automatically, the theoretical Carnot cycle provides us with practical problems. What do we do with that? Well, we have a modified now Carnot cycle, where you can see that we have pushed everything which is related to these devices here. We have pushed them all the way outside into the gaseous region. And here on the other side, for the pump, we pushed it all the way into the liquid region. Now we have a case where the pump operates on pure liquid and turbine works on pure gas. This is what we prefer. And also we can see from here that we give much higher efficiency of the boiler, and we allow the boiler to produce more steam, or rather produce superheated steam, raise the temperature higher. So if we have a higher temperature and a greater temperature difference between the higher reservoir and the lower reservoir, we have a bigger work done. Is it clear now? Now, this cycle here is called the Rankine cycle. Now, we can see it here as well, in a schematic, how the system is represented. And this gives us also another opportunity to present another interesting principle in thermodynamics, the heat engine principle. And there you can see, again, clearly from here that the higher reservoir and the lower reservoir, which is the boiler and the condenser, produce steam which passes through the turbine. And by the first law of thermodynamics, the work done, produced here, is equal to what heat is supplied from the boiler and what it goes down into the condenser. Now, this is a consequence of the first law of thermodynamics, but as you can see, the second law of thermodynamics restricts us in having all the work or all the heat converted into useful work. That the first statement of the second law of thermodynamics, which is the Kelvin-Planck statement, says that there's no engine that is 100% efficient and not all heat is converted into useful work. So this is one of the practical restrictions of the laws. And here on the other side is having to go from a cold reservoir to a hot reservoir. Again, here, the second law of thermodynamics, second statement, which is the Clausius statement, says that it is impossible, in order to go from a low temperature to a high temperature reservoir, we have to apply work. So in this case, as you can see, we have to apply work into the system, like the pump, for instance, and we have to go up. Now, as you know, the laws of thermodynamics have not been, they are not theoretical laws. They are based on empirical data and observations, and they have been, and since they have been developed in the 19th century, they are valid and they have not been challenged yet. So they are solid and they are there, and they provide us all the basis for this analysis. Now, the medium here, as you can, now we can see it here as well in the slides. Sort of representation is the same plant. So just to see if you can have a look at this case here, yeah, the hot reservoir and the heat is coming from a hot reservoir to a cold reservoir, and then work is produced. Now, if we change the efficiency of the machine, you see, the less the efficiency, the less work is coming. If we increase the efficiency of the machine, then more work is done. Now, if you go all the way down, the system says it's impossible. And that is the second law of thermodynamics. It is impossible to have 100% heat engine. If we go on the other side again now, okay, you can see that work is given into the system. To go from cold reservoir to the hot reservoir, we have to apply work. And also here, again, the amount of heat that is transferred from a cold to the hot reservoir depends on the coefficient of performance of this particular engine. This is also called a heat pump. It's a heat pump, as the name suggests, because it provides pumping of heat from lower to high. Now here, the medium at the moment, we talked about the power station, it is water, which converts into steam. But if we replace water with air, gas for instance, this automatically becomes a gas turbine engine cycle. And is again, you can use a gas turbine either to produce electricity, or in the other cases, the pump can be changed by the compressor, and it becomes an aircraft engine. So this is a compressor, the turbine, and instead of producing, turning a shaft in the case of an aircraft, it produces thrust. So this is one of the many applications of this heat engine principle. Okay. We have seen how we go around the Carnot cycle in a clockwise direction. Can we go the opposite way? Can anyone tell me if we can go the other way around? Yeah? Well, the answer is yes. The answer is, of course, the Carnot cycle is completely reversible, and all the processes can be reversed. In this case, of course, it's called the reverse Carnot cycle, but is most commonly known as the refrigeration cycle. Okay, as you can see, all the processes are reversed. Here, instead of having heat addition into the system, we had heat rejection, and this is when the system rejects heat either to another medium or to the environment. And here we have heat input into the system, which is where either we extract heat from a room or whatever. We will see how this works in a minute. Okay. Similarly as before, we have our TS diagram and the reverse Carnot cycle now on the TS diagram. And now the system is replaced by the compressor, the turbine, the condenser, the evaporator, and everything, say, works. In the case of the turbine, we have the compressor. In the case of the pump, we have the turbine. In case of the boiler, we have the condenser and the evaporator and things like that. Now, we still encounter the same problems as before. These components here, again, cannot operate in a mixture. They need to be, again, either in the gaseous or in the liquid state. And again, like before, as in the Rankine cycle, the reversed Rankine cycle, or vapor compression cycle as it's called, we push all this for the compressor into the gaseous region. Then we condense down into the condenser. Then we have to go all the way down to the liquid stage to have the expansion valve. There is the liquid stage, where we have the expansion device, and then we have the evaporator. The evaporator can be something like, in a room, extracting heat from a room, and the condenser is a device, a heat exchanger, which rejects heat into the environment. Okay. Now, this is a typical, the system here, we call it a refrigerator or a heat pump system. Now, what is a refrigerator and what is the difference between a refrigerator and a heat pump system? Well, both of them, they do the same thing. They operate on the reverse Carnot cycle. They both extract heat from a cold space. In the case of the refrigerator, we can see that it works if we draw this line as the surroundings, the refrigerator extracts heat from a very cold space, and by applying work input, and rejects it into their surroundings. And in this is a case where we call process cooling, and the refrigerator works only in cooling mode. The heat pump now, it does exactly the same thing as the refrigerator, but it takes, again, heat from a low temperature like the surroundings, and pumps heat into a warmer space like our houses. Again, using a work input, which is in this case is the compressor. And the heat pump now can work either in heating or in cooling, like in this case. And this is, as we said, the refrigerator can only work in cooling mode, which is a cold space, and throws heat into surroundings. Now, the heating and the cooling mode of the heat pump are the applications of human comfort and air conditioning. Now, in heating, you get cold heat from a cold environment and pumping into warm houses. Okay, and in cooling mode, we take heat from cold room and we throw it outside in the surroundings. Okay, here we have a temperature entropy diagram again of the refrigeration cycle. And we, as engineers, although we are nice people, we don't like too much to work with theoretical things. We like to have practical things in our hands. And the TS diagram, although is a very useful diagram to represent our system, indeed we prefer something different. We prefer the pressure enthalpy diagram to work with. It's another diagram which tells the same thing. But why do we prefer the pressure enthalpy diagram? Because of this quantity here, the entropy. Now, the entropy is a form of heat, as said. It's a quantity that you cannot directly measure. There is no such thing as an entropy meter. And we as engineers, we need to have something to measure. I mean, you cannot send somebody down an engine room and ask him to go down there and do these calculations to find something on the cycle. In fact, we prefer this one because we have the pressure enthalpy diagram. Now, what about this lady here, the enthalpy? Is that measurable? Do we have an enthalpy meter? No, we don't have an enthalpy meter either. But enthalpy is a form of energy which is easily calculated. As you can see, it is a function of a constant and two temperatures, any two temperatures in the system. Now, the constant is a constant, okay, we can ignore it. And now, do we have temperature meters? Yes, we do have temperature meters, and they are called thermometers. So we can go down the engine room with our thermometer and our pressure gauges, and we can easily identify the position and the state of our system anywhere on this diagram. Okay, this is the functionality of the pressure enthalpy diagram for engineers. Now, as before, the pressure enthalpy diagram, again, on this side is the liquid, that side is the gas. These two lines are the saturated liquid and saturated vapor lines. They all meet at the critical point. Anything above the critical point, the substance is in a plasma state, it's something different. And there in the middle, we have the liquid and the gas and the mixture. Okay, here we can see and say that the pH diagram is a function of different refrigerants in this case. So if here we have a very useful utility done by the Technical University in Denmark, which I would like to thank them very much for this interesting utility. So if we take a particular refrigerant, say, and we can easily create the pH diagram for this one, and indeed on this one we can even draw the refrigeration cycle. So if we go here and add the two reservoir temperatures, say -10, that's the room temperature, and this is the surrounding temperature, say 45, and this is the superheat, how much go into the gaseous region, and the cooling, subcooling, how much you go into the liquid region. If we put those numbers down, can easily draw the refrigeration cycle, and automatically from here, we can see that there is our compression process, which is completely into the gaseous region. And here we come slightly into the liquid region. This is what we want for our expansion device to bring it down to the evaporator. Okay, and this is something that we can do with different refrigerants. We can change different other refrigerants. We can take a mixture of a refrigerant, for instance. We can easily draw the pH diagrams and whatever. We can also draw the carbon dioxide type. This is the only refrigerant that we have at the moment that works in this area, the transcritical area. All the other cycles work below the critical point, which is the subcritical area. Only carbon dioxide works above the critical point, which is the transcritical area. Okay, that's a small example of how we can use the refrigeration. Okay, and here we come to see them how we can place the various components on the cycle. As you have seen before the cycle, here is a compression process in the gaseous region. Here we have the condensation, the condenser, which is basically a heat exchanger, which is uses to reject heat into the environment. Here we have the expansion device to lower the pressure and bring it into the evaporator, which is the indoor unit. And this is the one which extracts heat from, say, either a room or in the case of a refrigerator, this is extracts as a heat exchanger, which extracts heat from a cold storage room. And this is, now here we can see the subcool. This is how much we want to be into the liquid region. And this is how much you want to be into the superheat region. Okay, is that clear? Okay, a few little quantities here just to explain what you can get from the refrigeration cycle. We'll see much more later on in other lectures, but one of the interesting things I would like you to see here is this part here, which is called the refrigeration effect. This part, which is the difference of these two enthalpies or energies, it is the one which tells us the capacity of the particular refrigerant to extract heat at any time. And the refrigeration effect, is independent of any system, whether it's a small split unit or a big chiller or whatever. This is the same amount of heat is extracted. Now, what changes now, the capacity of the system, is when you introduce the mass flow rate into the system, the amount of refrigerant how much refrigerant flows into the system. Now, depending on the mass, if it says 1 kilogram, then a split unit, if it's a few kilograms, then this is what we call as so many kilowatts, or how many BTU per hour is a system, or how many refrigeration tons. This is the one which is system dependent. Okay, I hope this is clear between that one and that one. Now we come to a conclusion. We have now what we have done so far. The top part of the cycle, the power cycle, is when we have our Carnot cycle going the clockwise direction. Goes the clockwise direction, we have generation of power, we have electricity, we have motion, we have everything that moves in life. Okay, and on the bottom line here below, we have the Carnot cycle going the anti-clockwise, and in this case, we have human comfort, we have process cooling, we have heating and cooling, and all the things that we enjoy. So either way, these two cycles provide us with everything that moves in life. Okay. Thank you very much for watching the lecture. I hope you have enjoyed it. I think it will be a privilege to have you on board and explore even further this beautiful world of engineering. Thank you very much. I will now open the platform for questions. Is that okay?
Thank you very much, Mr.
Thank you.
Intercollege. Αριστεία στην εκπαίδευση.